Already computed the differential gain. Now we will compute the common mode gain, which is denoted by ACM. In this case, we will consider both the inputs are same and the VD is 0. So like the previous case, I will replace the VEE by 0 and VCC by 0, and as said, these two inputs are shorted together, or you can apply the same signal shorted together and a common signal is applied, that is VCM. So a common signal is applied, which is VCM, and all the DC sources are 0 in this case. Now notice here difference is, in previous case one branch current is increased and at the same time another branch current decreased by same amount. So as a result, in previous case, the differential case, one increased, another decreased, so this will be compensated. As a result, the total current was same. Now in this case, what will happen? Due to the same signal is applied and same voltage across the bases, if there is current IC increase, current through IC increased, this current IC will increase. So these two currents will increase at the same time. If this signal decreased, this will decrease, and same time this will decrease. So increase or decrease will happen at the same time, and as a result, the total current will not be same. In this case, the total current will be different. So if we consider that current is IC, so if we consider that current is IC and that current also IC, the total current through this RE is 2IC. So as a result, voltage across the RE is 2IC. So VE is equals, so that node voltage is VE. VE equals to RE IC. Now we can see that with respect to this branch, this will be looked as 2 times RE. For both the branches it is RE, but if I consider, if we want to see RE with respect to current IC, we can see it is twice RE. So that's why we shall replace this for the single branch. We will use the symmetry. And we will take a branch, and in this branch we will replace RE by 2RE. So the effective circuit for the single branch will be RC, that is VCM, and that will be 2RE, because for the single branch current is IC, and if I consider emitter current, collector current are almost equal, then we can consider that this current is almost twice of the IC. So with respect to IC, if I consider a current flow IC, same thing will be considered by doubling the resistance. So once you can double the resistance, or you can double the current to maintain this voltage. So in this case, we'll replace RE by 2RE. I'll repeat once again. This is happening because we are determining RE with respect to IC. So if it is 2IC, if it is 2IC, then it will be RE. For IC, it will be 2RE. So so we'll do this because this node voltage will be same if I make it 2RE. Now I'll replace this whole thing convert this whole thing into H parameter small signal model. So transistor equivalent H parameter model will be Now see, emitter, that will be my emitter, collector, and that base. Emitter is connected to 2 times RE, twice RE. Base is connected to VCM. So that will be ground, that will be this connection also ground, so we'll short these together. And collector is connected to RC. Collector is connected to RC, and we'll take V01 from here. So we'll calculate the V01. So that current is IC. If I consider that current is IC, so V01 will be V01 IC into RC. So V01 is IC into RC. Now IC can be computed as HAP times IB. So we can replace V01 equals HFE IB RC. Okay, I missed the minus sign because current flowing in this direction. So there will be there will be a minus sign. Now I need to calculate the IB. So if I use this loop, so writing the loop equation, that VCM equals HFE, say HIE into IB. So this voltage equals resistance into current plus this resistance to RE into, so current through this is IB plus HFE into IB. So IB1 plus HFE, or if I common the take the common the of IB will be VCM by HIE plus 2RE 1 plus HFE. So if I replace this here, the V01 will become V01 will be minus HFE into RC by HAE plus 2RE 1 plus HFE into VCM. So if I consider that HFE is much greater than 1, HFE much greater than 1, which is a valid assumption, then I'll 1 plus HFE will be HFE. So it will be equals minus HIE RC by HFE into RC by HIE plus 2RE HFE. Now this product, this 2RE HFE will be much greater than HIE. So 2RE HFE much greater than HIE. So I'll neglect this part. So it will be almost equals HFE RC by 2RE HFE into VCM. So HFE will HFE and HFE will cancel out. So remaining will be minus RC by 2RE VCM. So that will be V01. So if I take the ratio output by input, we can get the common mode gain. So if I take the ratio, if we take the ratio, that is V01 by VCM, it will be minus RC by 2RE. So that will be the common mode gain. That will be common mode gain, and it will be equal to SCM. It will be common mode gain SCM. And we are considering for the single ended output, as we always consider in practical cases. We'll see later that we consider output from single ended side, so that's why we are taking this. So that is the single ended output and difference and the common mode input, and for this case the common mode gain will be this one. Now from this we can calculate the common mode rejection ratio. In short, it is known as CMRR. So common mode rejection ratio is CMRR equals absolute value of differential gain by common mode gain. So differential gain by common mode gain, and it is equals differential gain we have already calculated. Note here that we are considering the single ended output, so that's why we'll consider the differential gain for the single ended output and consider the common mode gain for the single ended output. So for single ended output we already computed this part and this part, so it will be HFE by HIE and it will be equals HFE by HIE. So that is the common mode rejection ratio rejection ratio for the simple differential amplifier, which we have already discussed. And CMRR should be as large as possible. Differential amplifier should have very high differential gain, and as low as possible. Ideally it should be zero common mode gain. So ACM should be zero ideally, and ADM should be infinite very high. So that is the purpose for the differential amplifier, so that it can only it can only multiply the differential signal and nullify the common mode signal, and from this you can easily calculate the CMRR. So using this you can achieve CMRR not very high value. If you intend to increase the CMRR, this RE you can increase, because HFE dependent on the transistor parameter, HI also dependent on transistor parameters, but RE you can control externally. Problem is that once you increase the RE, the bias voltage required will increase. As a result, output voltage swing will decrease. So one thing you can do, you can replace RE by a current source. Current source having fixed potential across it, but it will force current if limited a certain amount of current. So 2 ampere current source will force 2 ampere from the circuit. So you can replace RE by a current source, so which will increase the CMRR by a great amount.